Hello. Today we're going to look at exponential decay functions, where exponential growth functions went up over time, decay functions go down over time, but you'll see lots of similarities in them. So to begin with, they're going to look exactly the same when I write this form, y equals a times b to the x. So notice the x variable is still in the exponent, hence the name exponential. We still have b for the base and a for the initial amount. That's all the same as it was before, so I suppose I should label them again. A is your initial amount. B is your base. And that number b, in growth functions, the b value had to be bigger than 1. In decay functions, though, it's going to be smaller than 1. Actually, it's going to be between 0 and 1. The reason for that is, well, we don't have negative bases for these. It makes something really weird happen. So we limit it to positive bases. So that's why it has to be above 0. And smaller than 1 is going to make it shrink. So it can be bigger than 1 to have growth. It can be smaller than 1 to have decay. What would happen if the b value was 1? Well, what's 1 squared? Still 1. What's 1 to the third? Still 1. What's 1 to the fourth? Still 1. So it wouldn't do anything to have a base of 1. You would still just get 1 over and over and over again when you raised it to different powers. So we don't use a base value of 1 for exponential growth or decay because it doesn't make it go up or down. Let's look at, for an example of this, let's look at y equals 1/2 to the x power. So notice my b value is between 0 and 1 because a fraction 1/2 is in that range. You could also see decimals here between 0 and 1. The a value would just be a 1. I could put an understood 1 out front if you wanted me to. I'm just going to leave it off. I don't think we need that. So let's go ahead and make a little table of these so we can see what this is going to do. So if I put an exponent of 0 in there, anything to the 0 power is 1. If I put an exponent of 1, 1/2 to the first power is 1/2. If I square it, I would get 1/4. If I raise it to the third, I would get 1/8. If I raise it to the fourth, I would get 1/16. Okay, now let's look at some negative values for my x. If you remember, a negative exponent, since my x is up in my exponent, a negative exponent makes you take the reciprocal of something. So I'm going to list these across from their positive values so you can see the similarity. So I'm going to put in a -1 for x. So if I have a -1 exponent, it's going to take that 1/2, the y value that went with the x value of 1, that y equals 1/2, and flip it upside down. So that's going to be 2 over 1, which is just 2. If I put a -2 exponent in, it's going to flip over the 1/4 and make it 4 over 1, which is just 4. If I put a -3 in, it's going to flip the 1/8 and make it just 8. If I put the -4 in, it's going to flip the 1/16 and make it just 16. So if I take those and decide to graph them, let's do this here. How about this one? Oh, I think my picture is going to be in the way, so let me add another blank page here. Oh! Don't know where it went. Okay, let's just add another one. Okay, so I'm going to put some dots on here. So when the x value is 0, we got 1. Oops. Let's see if I can make this bigger. 1. And then a 1/2, and then a 1/4, and then an 1/8, and then a 16th. Okay, and when I put the negatives in, it became 2, and then 4, and then 8. So it's gonna go like this, basically. That end part doesn't look very good, does it? Let me try that again. So this is where we should have an asymptote, which means it should be getting closer and closer to 0, but never touching it. So something like that. So it's the reversal of the exponential growth function that we saw yesterday. So it's going downhill as you read it from left to right. So that's what the graph would look like. Let's look at a similarity between what we saw yesterday with the rate given as a percent and what we could see with decay values. So this will look familiar from yesterday. You had y equals a times 1 plus r to the t power. The difference today is instead of something growing and it adding to it, if we have something that is decaying, this is going to subtract. So the formula looks almost the same. The a is still the initial value, initial amount there. R is still the rate. It's still generally going to be given as a percent, but then we're going to make it into a decimal. Make a decimal. And t is going to be time. Okay, so very similar to use. So let's do an example of this. Let's say that we get a new car, and new cars lose their value very fast. So we're going to say that this new car cost $28,000. And that the depreciation rate, so depreciation is how fast that car loses value. Appreciate would go up, depreciate goes down. So the depreciation rate is going to be 9.5% per year. So let's take that information and plug it into the formula that we just wrote. It's going to be y equals, so our initial value is the 28,000. So that's going to go in for the A. And then since we're depreciating, it's going to be 1 minus the rate. Now that 9.5, I need to take that decimal point and slide it over 2 places. Fill in the empty loop with a 0. So this is going to be 0.095 here. And then that's to the t power. So now we typically go ahead and simplify what's in that parentheses there. So I'm going to do that for you. So we have 28,000. Let's see, 1 minus a 0.095. That would be 0.9. Right? 0.9055. Yeah. To the t power. So, so we've modeled the situation with an equation. I haven't asked you anything about this yet. So let's say we're wondering, when is this car going to be worth $20,000? It's going to lose money. When's it going to be down to $20,000? So the way we're going to do that is with the graph of this. So let me go over here to Desmos again. And let's model this. So we have y equals, it was 28,000 times 905 to the x or t, whatever. I'm going to put an x there. Oops, x. So I need to scroll out so I can see this thing. It's going to be way up here because I have such a high initial value. Okay, I don't know if you're going to be able to see me do this. You won't because of my picture, but there's a wrench up in the corner of Desmos. I'm going to click on the wrench and it's going to let me change my numbers instead of just zooming with my fingers. So I want my x-axis to go, let's go from 0 to 20. And my y-axis, I want it to go from 0 to, well, let's go 30,000 since our car's initial value was 28,000. Okay, so sometimes that's easier. Okay, so I have 28,000 up here is how much the car was when we first bought it, brand new. And I was wondering when it was going to be worth $20,000. So would I look for the 20,000 on the x-axis or on the y-axis? Well, your independent variable here is time. So I want to know that when the car is going to be worth $20,000. So that 20,000 is going to be a y value. So I'm going to put y equals 20,000 so that I get that gray clickable dot. I can click right there. And you see this x value that's popping up of 3.371? That means in 3.371 years, so just over 3 years, 3 and a third years, that car's value is going to be down to $20,000. I spent $28,000 on it. Now it's only worth $20,000 because of depreciation. So that is how you will use this to model situations. So, okay, that's everything. Remember that Jesus loves you, and so do I. So do your math.